So we are going to finish off your family tree. We are going to learn about kites today. Have you ever seen Mary Poppins, the video where they go, "Let's go fly a kite"? Maybe, maybe not. This is a picture in the background of the Austin Kite Festival. They have one every year. Look at all those kites. Everyone just shows up and flies a kite. Pretty fun. All right, let's figure out what the properties of a kite are. Show you the video at the end. Instead of me just telling you the properties, I'm going to show you a real-life kite, an actual polygon that's a kite, and I filled in all the values. So I want you to look at those segment lengths, and I want you to see if you can write the properties yourself. Okay, hopefully you had enough time to really study that kite. So what are some things that you notice? You know, in a parallelogram, opposite sides were congruent. In a kite, are opposite sides congruent? No. What's congruent in a kite? What's that weird word that means like in a row? Next, yeah. Consecutive sides are congruent in a kite. How many pairs of consecutive sides are congruent? Because these are consecutive, but they're not congruent. How many pairs of them? Very good. We've got some consecutive sides congruent, 2 pairs of consecutive sides. All right, what about those dotted lines? What about those diagonals? Are they bisecting each other? Because in a parallelogram, they bisect each other. Well, they can't bisect each other or else it would be a parallelogram. But look at that. 12 and 12. That wasn't a coincidence. So one of the diagonals bisects the other. Good. Anything else you want to notice about these side lengths and segment lengths? So you guys are saying the diagonals seem perpendicular, but we don't have any numerical evidence to support that. Do you notice that those are maybe Pythagorean triples? Have you learned some of your triples? 5, 12, 13, 12, 35, 37. You may or may not have noticed it. If you did notice, those are Pythagorean triples. Pythagorean triples only occur in what kind of triangles? You're right, Pythagorean triples only happen in right triangles. So we might have some right triangles on our hands. All right, let's look at how the angles are working. You were right, look, you guessed it, it really was 90. Take a look and study those angles and see what conclusions you can draw. All right, here we notice this angle has been bisected, and this angle has been bisected. But those angles aren't congruent. Look, this one's 40 and this one's 20. So I don't think we have any for sure parallel lines in a kite, so we need to be careful about that. But I do notice that in both pictures, this diagonal is like a mirror. It's like a mirror image. Look, 20 looks in the mirror and sees 20. 70 looks in the mirror and sees 70. 80 sees 80. 10 sees 10. What is something called when it acts as a mirror? Symmetrical. Very good. So did that work in this kite as well? Was this a mirror? Let's see. 12 looks in the mirror and sees 12. 13 looks and sees 13. Oh my goodness. So it's looking like one of the diagonals is a line of symmetry in this kite. All right, let's go ahead and dive into the properties so we can do some practicing. The definition of a kite, don't write this down yet. It is a quadrilateral, so it's a 4-sided figure with exactly 2 pairs of consecutive congruent sides. The definition is always property number 1. Property number 1, 2 pairs of consecutive congruent sides. Next property, diagonals are perpendicular. Hey, the kite stole that property from someone. What other shape has perpendicular diagonals? Yeah, rhombus. So you know, sometimes, you look like your brothers and sisters a little bit, but sometimes you have some qualities in common with your cousins. Well, the kite and the rhombus aren't in the same side of the family tree, but they could be cousins. They could have something in common with their cousin, a certain feature. So yeah, a rhombus and a kite, both of them have diagonals that are perpendicular. All right, this is not a property, so don't write this down as a property, but one of the diagonals, there's 2 diagonals, one of them is always going to serve as the diagonal of symmetry. You'll be able to tell just by looking at the picture which one it is. I would say 90% of the time, 9 times out of 10, it's going to be the longer one, but I don't want to say that it couldn't be the shorter one. Now, to me, that's a weird-looking kite. It's not very often that it's the shorter diagonal is the diagonal of symmetry. It was actually really hard for me to even draw that figure in my software because I'm just not used to seeing kites like that. But one of the diagonals is the diagonal of symmetry. And by the tick marks, by the angle markings, you'll be able to tell which one it is. Okay? Now, that diagonal of symmetry does 2 things. That diagonal of symmetry does 2 things. It bisects the other diagonal, and it bisects the angles. So it really cuts the whole kite in half is what it does. Write these down. All right, let's solve some problems. Solve some kite problems. Draw this picture somewhere in your notes. Make it a little bit larger. And yeah, we're going to find angle 1, 2, and 3, but we're going to find all the angles. We're going to find them all. I'll give you a second to draw it. Okay, so how this kite works, remember what I said, and this is the most important thing about a kite. One of the diagonals is the diagonal of symmetry. You can tell by the tick marks. So I would love if you get a highlighter out or maybe another colored pen out or anything you have and highlight the diagonal of symmetry. The reason I like you to do that is because then you're not having to memorize properties, guys. I don't have to memorize those 4 properties. I just have to know how to use a mirror. Mirror image. If this is 27, well then, oh my goodness, this is 27. If this is 14, then this angle is 14. Now, I do have to memorize the property that the diagonals are perpendicular, but the good news is they'll always look perpendicular. In a kite, you can't really make the diagonals not look perpendicular. So, we've got 90, 90, 90, 90. And then, of course, now we have 4 right triangles. And we know how to find a missing angle in a right triangle. We know the shortcut even. We can just take 27, that looks like a teepee, and we can subtract it from 90, right? 63. And then we can go over here, and we can take this right triangle, and we can take 14, and we can subtract it from 90. Right? So, 76, mirror image, 76. 63, mirror image, 63. We're seeing how that works? If you were to flip it over, whatever angle it would land on is congruent to that angle. Okay. Let's try one with some sides. Quadrilateral kite is a kite. I know I got really creative here. IE is 30. KI is 25, and KT is 56. We're going to find all the missing segments, actually. Of course, we're going to find those using our favorite theorem in the whole world, Pythagorean theorem, because, of course, those are right triangles, just like in a rhombus. And thankfully, Miss Tanton has one of my favorites in my internet or my Google Chrome. One of my favorites is this site that lists tons of Pythagorean triples, which means I am making sure that you're getting whole number answers instead of having to factor tree like crazy, right? So you're welcome. All right, let's work some of these. First of all, I want to identify my diagonal of symmetry. This is the diagonal that cuts things in half. Did the 56 get cut in half? No. But did my mouse is on it. Did the 30 get cut in half? Yes, it did, because KT sliced the kite in half, okay? So this is 15, 15. So now I can do Pythagorean theorem with this triangle right here. 25 squared minus 15 squared. You get 400. You square root 400 and you get 20. KS is 20. Alrighty, now we use the segment addition postulate. I know you don't know that that's what you're using, but KT is 56. KS is 20. So what is ST? 56 minus 20? 36. So now we have ourselves another right triangle. 30, 36, and X. So now we can do Pythagorean theorem. 30 squared plus 36 squared, and take the square root of that beautiful number. Not 30, guys. Not 30, not 30. Sorry, 15. I know what I'm doing. 15. 39. And of course, it's a mirror image, so 39, 39. So IT is 39. SI was 15. So, lots of right triangles, lots of Pythagorean theorem, lots of segment addition and subtraction. I don't think we need to do another angle one, so let's do this one. Quadrilateral ABCD is a kite. Look at that. We have an angle, and that's not just a plain old angle. That's a special angle, right? Because if you look at this triangle and you're like, I can't do Pythagorean theorem with just one side, then you have to dig in your toolbox for something we haven't used in a couple weeks. Yep, you have to dig in there for that 30, 60, 90. And that's on your formula chart. You don't have to memorize it. X root 3, 2x. 14 is across from the 90. So across from the 30 would be 7, and across from the 60 would be 7 root 3. Let's see if we can fill in all these angles. EAB, 30. ADE, 60. EAD, 30. AE, 7 root 3. BE, 7, and BD is 7 times 2, because we know that that segment was bisected. Okay? Okay, last one for today. We've got Allison. She wants to build a kite. Have you ever built a kite yourself? With the crossbars and everything? She has 3.5 feet of piping for the border. I feel like border is spelled wrong. Anyways, in diagonals of the kite, maybe not. If the length of the long diagonal is 1 foot, given the information on the picture, does she have enough piping to build her kite? I'll let you think about that one before I start solving away. Let's get the most important part over with, which is we don't want to be in feet and inches in the same problem. So let's just take care of that. Let's convert everything to inches since our figure already has some inches on it. So she has 3.5 feet of piping. So we want to do 3.5 times 12. She has 42 inches of piping. That needs to cover this, 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 and this. She's using piping for the border and the support, the diagonals. Let's fill in everything we know. That's 3, so we know this is 3. Ooh, do you know your Pythagorean triple? 3, 4, 5. 3 squared plus 4 squared is 5 squared. And then we haven't used this yet. The long diagonal is 1 foot. Well, 1 foot is 12 inches. 12 minus 4 is 8. Okay, now we need to find MN and ON. This is not a Pythagorean triple. 3 squared plus 8 squared. So it's the square root of 73. It's a real world problem, so I give you permission to round. I give you permission to round. Or you could just call it square root of 73. Okay, let's add it all up. How many feet of piping does she need? I'm getting 45. Are you guys getting 45 when you add up all of those segments? So let's see what the multiple choice says. No, because she needs 45 inches. That sounds pretty good. Yes, because she only needs 40 inches. Uh-oh. C, cannot be determined with the given information. All right, that was a weird problem, but it's good to practice problems that aren't just fill in the blank, that make us think a little bit differently, right? The answer was A.